Okay, hello. Today we're going to talk about torque. Okay, torque is an interesting concept because we actually see it in our everyday lives. Okay, torque basically is we see all physics mostly in our everyday lives, but to be honest with you, this is very conceptual, and that's what I love about it. It's very visual. So torque is a rotating quantity. It's a vector because it's force times radius, right? It's the force times the distance, basically of a lever of an object. Okay, we see torque mostly with levers, and anything that rotates basically has torque to it. Okay, so we have a force times a radius. We're gonna say it's the quantity of force, which could be equal to mg, ma, whatever it may be, depending on the situation you're in. Okay. However, torque is force times the radius. But the most important thing we need to realize is that the angle actually affects our torque. Okay. So the angle at which our torque is at really affects it, because what will happen is it'll cancel out these vectors. And I like to look at free body diagrams when it comes to torque because, like I said, it's so conceptual that free body diagrams really make it easier to understand and easier to visualize. Okay, so basically, we say it could be mg, ma, whatever it may be, and then we're going to say times sine of theta. It's our y component, sine of theta. Okay, so if I have a lever, I have a lever coming out. All right, and basically this is my radius from my pivot point, right? This is R, okay, because this is my pivot point right here. Okay, and it can rotate this way or this way along the pivot point, right, depending on where our pivot actually is. But the most important thing we understand here is that our radius is this, and that when I exert a force on this radius, it actually has to be at the end of where it is. So let's say this is 22 centimeters. The force is at 22 centimeters. That's my force applied. And in this case, we'll say it's mg. We'll put a box at the end, right? And we'll say that this is mg acting down if I would draw a free body diagram. And that we have mg and fn over here, right? This is that same mg, and this is our fn, plus our mass, plus ma, right? Because this is accelerating. But let's just say it's not accelerating. Let's say it's at equilibrium somehow. We have enough friction in here that it's at equilibrium. We have this force coming down times our radius, okay? The whole thing I'm trying to get across here, the whole point I'm trying to get across is this vector right here, okay? To prove sine theta. As we know, force times the radius, which is very simple, it's plug and chug. But times sine theta, and I want to explain why it's times sine theta and not cosine or tangent. The reason why it's times sine theta is simply because when I split my components up and I look at my free body diagram, right, I got this box, I have force going down, right? Now, if I were to look at my forces, if my force is going in this direction, right, theta is equal to 90, right? Does that make sense, right? That's 90 degrees to the parallel, or to the perpendicular, actually. So this is 90 degrees, right? So my y component, it's only a y component in this case. There's no x component, right? There's no x component. But there is indeed a y component, right? So sine of 90 is actually equal to 1, funny enough, right? If I do sine of 90, it equals 1. So 1 times my force times my distance is 100% efficiency, right? It's 100% efficiency, right? So basically what I see here is that I'm getting 100% efficiency out of my torque. It's a better mechanical advantage in this case, or a disadvantage depending on what the situation is. Okay, but in this case, that equals my torque. Now, in a different situation, I may have something more like this. And this is why I like to look at the free body diagrams, because it really comes together and makes sense here. Here's my cube, but let's say I have this coming in at a 30-degree angle, right? So this is my force applied. So in this case, it can't be mg really, because it'd have to be, unless if you had this on an angle. But so basically, I have my force applied coming in on this cube. But now in this situation, though, however, in this situation, my y component goes this way. I have a y component going this way. And I have an x component going this way. Well, actually, let's write y here. Y and an x, right? If I were to split this up, this is theta of 30. So theta equals approximately 30 degrees, right? My x component, though, is canceling on this axle, right? So my x component is actually canceling, and it's not moving because this axle is stationary, right? This axle is stationary, right? So it's not actually going to move in that direction, but it's going to move in the y direction, okay? So basically what we're seeing here is it's working against the axle. My axle is applying a force in this direction, while I'm applying a force, right? This is the force applied, we'll say force A, right? Force A times, what is it going to be in this case? Well, it's going to be my adjacent over my hypotenuse. So cosine, force times cosine theta is what's counteracting with this. And these two have to cancel for it not to move, right? Those two forces actually have to cancel out for it not to move in the x direction if I'm looking in the x. Now, if I look in the y, I'll do that in blue. If I look in the y direction, forces aren't going to cancel here because the lever is going to start moving, right? This was going to not be in equilibrium. This will start moving and start rotating in this direction, which means that my x's cancel. However, my y's do not cancel. I have an acceleration in this direction. Well, actually, it's tangent to the circle, right? Because it's going to keep going in this direction. I'm going to constantly get an acceleration. Well, I'm also going to get a centripetal force, really, in that direction. But this would be centripetal acceleration, and this will just be my acceleration of my object. But in this case, my y component is not supported, whereas my x is. So it's going to cause it to move, all right? And the lever is actually going to go down, but this x is causing it to be bound to a certain point so it doesn't move. So now the x doesn't cancel. So this is force times sine theta, force applied times sine theta, right, is my y component, right? And then force applied times cosine theta is simply my x component, okay? So we see here that is going to be a smaller sine, or I mean a smaller y component than there is an x, right? X is going to be small, x is going to be greater than y is going to be smaller than x, right? That's what that means. So essentially here, we're going to be looking at more force canceling in the x direction against this pivot point right here, okay? And that's why I really like to show this example, because it really shows conceptually what's going on with torque, okay? Because most people just think, oh, they don't realize that this is actually canceling, and it's very interesting because you don't really think about it. But when I'm pulling on a lever, just like when you go to open the door, right? You go to open a door, the door looks like this. If I push on the handle in this direction, this hinge right here that's holding the door to the frame, right? It has to combat that force in the x direction, right? So that has to combat that x, and then, or my y or whatever. Now this component is going to drive it forward. So that's why this is much smaller. This is going to be much greater, right? Because it has to combat, these two cancel. X has to cancel for this door frame, this door not to move side to side. However, the door is going to want to go this way, but it's going to take a curved path instead because it's bound to this point, this pivot point, right? So it's going to want to take a curved path. It gets restricted in this direction. It's going to want to pivot upon it because this is restricting it from moving this way. Just like if I were to push an object like this, it moves. When I restrict its x direction, now the y is going to take over and push, and then the x and y obviously switch here, right? So it's going to be stuck here, and it's going to keep moving about that pivot point because nothing's canceling the force in this direction unless there's an opposing force, right? That's forces and the law of conservation of energy, or the law of conservation of momentum, however you want to say it. But I believe, actually, that's one of Newton's laws, that an object will not stop moving unless there's an opposing force, or, there has to be an opposing force for it to stop moving. Obviously, there's friction in this case, but besides there being friction and air resistance because of the door, swinging open and closed, there also has to be an opposing force canceling out that y component. And in this case, there isn't. That's why the door is allowed to move and pivot about that point. Okay, so really quickly, I brought in a little prop from the garage. I brought out a torque wrench, and it's very interesting, and you might think this is boring because who wants to learn about torque wrenches in the middle of a physics video? But really, a torque wrench is an excellent example, okay? It's an excellent example. And the reason is not just because it has the word torque in it and we're learning about torque, but a torque wrench, actually, the interesting thing about this torque wrench is that it has a very long lever for a reason, and that's why I'm going to go into depth, because there's a lot you could actually talk about with torque wrenches, okay? I didn't really think about it until now. But there's actually a lot we could look at when we think about torque wrenches and torque, which we're learning about, okay? So with the torque wrench here, we actually see that this lever, okay, see it ratchets in one direction, and the other direction it locks, okay, and, whatever, woohoo, But the important thing about this torque wrench, though, is that we don't realize is that not only does it lock, but it actually, the lever of it is extremely long, and that's what's interesting about it. You see this lever, it doesn't even fit in the canvas. That's why I had to move the camera away to show you the length of it. This lever is extremely long, and for what reason? To get a lot of torque, because look, I put my hand here, my hand cannot combat the force I'm putting out here. Even here, there's so much torque on this because this is a small diameter, okay? As I get grease on my hands, but this is a small diameter, right? And this is a huge diameter, and it's also very, very heavy, right? It allows me to get a lot of acceleration on my twist. So the interesting thing about a torque wrench, though, is there's special things about it that make it different from a normal wrench. Not only is it a long lever and it's heavier, but this mechanism right here actually allows it to click at a certain torque. And in this case, I don't have enough muscle to do it. Maybe I will. Let's see if I can do it. But it'll click. Ooh, it's really set high. But it'll click at a very, very, it'll click at the torque it is set to. Okay, so we could set this into foot-pounds. In this case, we have foot-pounds, okay? Torque is measured in foot-pounds. It's also measured in Newton meters. It's measured in a lot of different units. But see, I have 150, 30, and I twist this little knob, and it gets lower and lower because there's a spring mechanism in this shaft, okay, that's actually pushing on this or pulling on this mechanism, right, giving it the pressure. So when up there it goes. Hear it clicking? So basically what happens here is once this clicks, I know I'm at the right torque, basically. And then as I turn the handle back up and make it tighter, it won't click now because it will require a lot more force for it to click as I damage the table. But so basically the idea we're trying to get across here is that this torque wrench will click at a certain torque. Why? The reason why it clicks at a certain torque is because it clicks at a certain force. It clicks at a certain force, which allows it to basically cut off, when to stop turning it. So the forces will cancel in this case. Okay, the forces amongst the spring mechanism